Thank you, Hans. Ladies and gentlemen, it is a great honor for me to speak about ocean grids around Europe. And I started my presentation with a slide with a quote from The Economist roughly 1.5 years ago. And it was an article about, as they tell it, a grandiose plan to link Europe's electricity grids. It's both the European grid, the European supergrid, with wind power. And basically I showed you this picture because I want to show you that when magazines like Economist start writing about these issues, then you might think it could be gaining some serious attention. So let me guide you through the presentation. I will address in this agenda for today 5 questions. So first of all, the introduction. Why is this topic, ocean grids, of interest for Europe? What are renewable energy production trends? Of course, some of them you might know already, but it's good to recap. And then thirdly, what are the challenges for the European electricity grids? By the way, this talk, ocean grids, focuses of course about Europe. And then the fourth question, what is the concept of an ocean grid around Europe? And how can we get there? What could be a transition path towards ocean grids? And finally, I would give a conclusion and some future outlook. Just starting as an introduction, why is this a topic? As you all know, the European Union and the individual countries have policies to encourage renewable energy sources. It is written down amongst others in the Green Paper of 2006, and one of the goals is to reduce the dependency of imported oil and gas. Then you also might know that there is a European Smart Grids technology platform that focuses on the issue of how to connect large amounts of distributed and concentrated renewable energy sources into the grid. And then a third very important reason is the prevention of blackouts. I have here a picture of a report which is called Lights Out in 2009. It's an American paper, but it fairly illustrates that this is a topic which is becoming increasingly important because we as citizens become more and more dependent on electricity, and basically this prevention of blackouts calls for a European transmission coordination, basically more interconnections. And then moving to renewables, offshore wind power is an essential element in this to reach it. EWEA, for instance, estimates that roughly some 120,000 megawatts of wind power has to be built next 20 years and will be built. By the way, just as an illustration, at the moment we have in Europe roughly some 560 gigawatt installed power, installed generation, and that means that during the next 10 or 20 years this will increase to roughly 1,000 gigawatts, so that means that the wind power will have a share of roughly 10%. And last but not least, the technology matures. Wind turbines become mature technology, and also high voltage DC and especially voltage source converters is a technology which becomes increasingly more mature. By the way, as some of you might seen, I'm active in the quality assurance of ultra high voltage DC, and that means at present I'm working at projects in China where we deal with roughly 6,400 megawatts plus and minus 800 kV and transmission distances up to 2,000 kilometers. So that's the classic HVDC, but it still indicates that the technology is becoming mature. When we look at the production trends of renewable energy, we can focus on wind resources offshore, and then you see in the picture in the right roughly the build-up of the world wind power shares, and you can deduct from this that Europe has roughly a share of 50%. Apart from wind power, wave and tidal energy is under attention of European Union and individual countries. And also you can imagine that things like underwater turbines, production of aquatic biomass, you mean algae, to generate electricity, of course, or even things like what is called blue energy, using the electrical potential between fresh and salt water, can be used to increase the share of renewable energy. And at the moment, wind power in Europe, just to summarize, it's only roughly some 40 gigawatts plus, that means between 40 and 50 gigawatt, and only half a percentage is offshore, and that's all in shallow water, less than 50 meters. And by the way, just as an indication, offshore wind power is roughly, ballpark figure, 50% more expensive than onshore wind power. Continue. We can see here a picture of the average wind speed in and around Europe, and as you can see that there are areas where quite some large and high wind speeds are available near the British Islands, Great Britain, Netherlands and the North Sea coast, but also in the region near Spain and in the Mediterranean. And a lot of countries in Europe have quite ambitious plans to erect and construct large wind farms, offshore wind farms, just to mention a few: UK, Germany, Netherlands. And as an illustration, I have a picture included of Hornsrev, the Danish offshore wind park, which has a capacity of about 160 megawatts. You can imagine that if we are going to build large offshore wind powers, then perhaps there is a need for storage, and probably we can't disconnect large amounts of renewable offshore wind power with storage, and for that reason companies like my company has invested in research into the feasibility of what is called an energy island. And you must imagine, I'm from the Netherlands, and people in the Netherlands are very good at building dikes and keeping the water out of the land. So what did we come up? We come up with what we call a hole in the sea. That means we built a dike outside the dunes in the North Sea, and we can reduce the water level of this artificial island, within this artificial island, from say up to -30 or -40 meter, so pump the water out. And you can imagine, if you fill it up, you actually have a hydropower plant, and in general the capacity will be around 1.5 to 2 gigawatts, and it's good for roughly 15 hours, 10 to 15 hours. And of course this is a very expensive project, so that means that probably it cannot be funded. So we thought of it and having it additional 500 megawatt wind power along the dike of the island, and perhaps some industrial activities like liquefied natural gas terminal. Also can imagine that instead of doing this, we could also harness the the hydropower of countries like Norway. And actually in the Netherlands we did so. We built a DC cable, the so-called NorNed connection, which connects the Netherlands to the Nordic electricity grid, and that can be used to fill the reservoirs, the water reservoirs, and pump the water up and down if needed. And of course a lot of money is made with this scheme. Why am I telling you this? Basically because of the coming of renewable energy, we change basically the scheme which is happening in the networks all over Europe. In the old days it was very simple. We adapt the generation to the demand. If the demand increases, we increase the generation with the central power plants. But now, ladies and gentlemen, with large offshore wind power farms coming up, all renewables like solar, we have to adapt the demand to the production. So there must be a way to get rid of all those electricity surpluses, and you can imagine that you can do it with large-scale storage or other means. Continuing, we come out with what is called, what are then the challenges for the European grid? What's happening? Of course, there is the Trans-European Network Initiative, which was launched in the 80s at the European Union, which called for single markets. And one of the issues is of course a single market for energy networks, gas and electricity, the so-called 10E. So that's a challenge, how to achieve that. To achieve that, of course, there is more transmission and cross-border capacity needed. Just as an illustration, this is a picture of the cross-border, the physical cross-border electricity flow of the UCTE in 2007. Just to have an idea, that means that physically through Europe roughly 10% of the 2,500 terawatt hours used physically crosses borders. That means we're shifting huge amounts of electricity through Europe. And you can imagine, if the European Union wants to have a real transparent electricity trans-European energy network, then probably even more cross-border flow will happen. Just remember, ladies and gentlemen, in Europe some 10 or 15 years ago there was zero cross-border physical flow, except when there was an emergency in one of the neighboring countries. Then there was some assistance from the country, but the law said you had to solve your problems in your own country within 15 minutes. So the network, the interconnected network designed for assistance, actually evolved into a transmission network, which has to facilitate large power flows through Europe. So, and of course this needs reinvestments and investments. Then, ladies and gentlemen, what measures are needed for the integration of massive amounts of wind power? You can imagine that the transmission capacity on the mainland has to be increased, because if you generate that electricity you have to get it to the load centers. By the way, this is one of the issues, I put it as a first bullet, which is often forgotten. You can imagine people think about, okay, we have to switch to renewables, but then forget that you not only have to do something on the on the sea or on offshore, but also on the mainland. Then of course there is the problem of controllability of the wind farms. We want to have some way to control the output. I sometimes formulate it as follows, because there are some requirements, network connection requirements of wind farms. The wind farms have to mimic old-fashioned power plants and have to fulfill all their same criteria and technical capabilities. But perhaps we have to switch from that idea in the future. Then of course, if we have wind power, which fluctuates, also have to have fast acting generator units that can adapt to those rapid changes and fluctuations in demand and or renewable energy production. Logically, what if the wind doesn't blow? Of course, you might say, but there is always one or two places in Europe or in a large area where the wind blows. Agreed, but still it is impossible, physically impossible, to have wind power generated, say for instance in Portugal, and have it instantly transmitted to, say, some place in Poland or wherever. So that cannot be done entirely with interconnections. Or, as some people may say, it's possible, but then we need more or less a copper plate in the bottom, in the soil of Europe, and then we can do it. But that's of course an illusion. As told earlier, energy storage units can be a means to adapt demand and power production. Actually, it's if you're looking at the developments of battery systems at the moment, it's going quite fast, and it's powered by developments in like computers and mobile phones. So the small batteries, there is a big technology development, and perhaps bigger systems come also online. Just as an example, a few of my colleagues recently were in Japan to do a factory acceptance test of a 4 or 6 megawatt battery system, which will be put online. Then of course, what was done in the old days, sharing of power reserve between countries. When a country has a problem, other countries can help and sell that, of course. Then sometimes, from system point of view, you have to curtail the wind power production. Like you can imagine that if you have too much wind, for instance, at a certain instance, you get system instability, so you have to curtail that in one way or another. System based. And there's a lot of progress been made until now into short-term forecasting methods for wind power, because we want to know in advance how much yield the wind farm will get. So forecasting. And you can also imagine, ladies and gentlemen, that at the end probably the optimal solution will be a mix of all those measures, and then we are able to integrate massive amounts of wind power and achieve our sustainability goals. When thinking about this, ladies and gentlemen, we can think of smart grids to accommodate and facilitate this. And a lot of people think smart grids are only dealing with distribution grids, but it's not true. Smart grids are also transmission grids. And just as an illustration, I copied a picture from the Global Energy Network Institute, which is roughly some 30 years ago, which was founded 30 years ago. They had a vision of interconnecting the whole of the world with high voltage DC lines, electricity connection to all over the world, just to electrify all the countries, to bring electricity also to rural areas. And based on that, you can imagine that when you think about, okay, how should we do that, how should we reinforce the mainland electricity grid, that you can think of an electricity superstructure, a supergrid in and around Europe as shown in the picture. And probably this will be a DC grid. Why DC? You might know that when the distances become larger, overhead distances become larger than roughly 600 or 800 kilometers, it's very difficult to do this with AC lines. You have to compensate, with DC lines, transmission distance is of non-importance. So you will see in countries like China and India that the long distance transmissions are always HVDC, point-point transmissions. AC structures within Europe, the main voltage level is roughly 400 kV, and that limits the transmission capacity. So, and the next step, say up to go to 560 or 750 kV, is not likely at the moment in Europe. I know there are places in the world where higher voltages than 400 kV exist, and I personally was also involved in the project in China with a demonstration line of 1000 kV AC, but I can assure you, ladies and gentlemen, that is very complicated technology, and compared to that, DC, long distance transmission, is more or less mature. So far for the introduction and the reason why, ladies and gentlemen. Now we come to the point, what is the concept of an ocean grid? Basically, an ocean grid or a sea grid has two objectives, and I'll start with the second: provide connection points for offshore wind power stations. This is typically where it starts, because people think of, the way of thinking is, okay, we need offshore wind power, so we have to connect that. Why not do that and see? And just as an illustration, I showed you a picture taken from Airtricity, which develops also the concept of a sea or ocean grid, and you see all ocean-like structures, and often the point backbone for the mainland, say how to back it up, how to solve that, that's often forgotten. So basically we think that an ocean grid should have two objectives, and the connection point and the backbone for the mainland. As said earlier, the technology which has to be used will be HVDC because of the length and power. It's physically impossible, it's not, I must admit it's not impossible, but it's physically very difficult to transmit AC power through cables which are longer than, say, 30 or 50 kilometers. So when you talk about submarine cables, you will soon get up with HVDC cables. And then there is another problem, of course. If you think about classic HVDC, that means with thyristors, and thyristors can only be switched on, so the switch off is during natural current zero. You have to, if you have to reverse the power flow, you have to reverse the voltage. And that's, of course, for cables a very severe stress. For that reason, for the classical DC, power cables are often what are called mass impregnated, heavy, and the oil and the mass which insulates the cable is capable to deal with those voltage switches, those polarity reversals. When you really think about building an ocean grid, you probably want to have voltage source converters. This means you will have to easily switch from one direction of current to the other direction of current, and that means you keep the voltage the same. And keeping the voltage the same, that's nice, because then you can use extruded cables. And of course there is the problem with classical DC. It's difficult to build what's called multi-terminals. Say a take-off point, a T-point is difficult to build. With voltage source converter technology, it's very easy. Just how does an ocean grid look like, or how might it look like? Here you see an impression for the North Sea, and there are three things you might notice. You have land terminals, the yellow dots. You see this grid is connected to several ways to the land. Basically the transmission between the what's called hubs in green with a capacity in gigawatts ranging from 5 to 2 is a 10 gigawatt. While why 10 gigawatt? You can imagine if you have a cable, a transmission cable, which has only a capacity of 1 or 2 gigawatt, it's not enough. You cannot connect a lot of wind power to that, and especially if you want to make a grid. As you can also see, there are several paths which can be followed through the ocean or through the sea, and also you can see that a parallel path can be made from a country, say for instance in the north of the Netherlands, go outside and go back to the load centers in the west. So these things are possible. And if you have such a grid, you can imagine that you also can connect oil platforms which might have emission constraints, or do that because they want to save some space, because they want to focus on a core activity, oil drilling or gas production. You can also think of the big number of what's called marginal gas fields in the North Sea. Actually, these are gas fields which have too little pressure and are not economically connectable to the high pressure gas pipelines. But some of those wells have a capacity of say 200 megawatts for 10 years. So you could put up a smaller generator and extract the power from that. This ocean grid in the North Sea continues of course with Southwest Europe, and then you see a focus on the areas where between Italy and France, where the highest wind velocities are, and also in the region southern France and Spain. But you can also see a connection, in a yellow connection, with North Africa, and this might be interesting. You can imagine that schemes are on the way where large-scale concentrated solar are being developed in Northern Africa and connected to Europe. As seen from this, ladies and gentlemen, you can imagine that it will be a huge investment, and as seen from this point of view, this should be considered as deep connection cost for developing this, because it's not possible to ask for a developer to pay those costs. A single wind farm developer simply says, okay, if I have to pay a cable, I make a direct line to a connection. This should be there in place. You can imagine this should be a task of the government or for the TSO. Ladies and gentlemen, when talking about such an ocean grid, you can imagine that if we would have such an ocean grid and the European supergrid, this would really significantly contribute to the single European energy network, the 10E network. And as such, it would be very good for transparency and for market sharing and improvement of integration of renewables. But, as always, there are some requirements. One of the big challenges and requirements is that there must be some sea deployable transmission systems with really large capacity. We have to have cables with ratings between 5 and 10 gigawatts. That is, by the way, 5 to 10 times higher than the present state of the art. Due to a lot of production, we get the benefit of economies of scale. We don't have it now. Of course, one of the big problems with cable landing points is that you get a congestion of cable landing points, because the number of landing points is very limited. You can imagine, especially in a country like the Netherlands, which has 50% of its surface below sea level, people are very cautious when you say we need a dune crossing for a cable connection, because we don't want to have holes in the dikes, even not when there's power coming in. Then of course, underwater cable routes, probably there is a shortage of them, because we found out, and you might know, that the sea is very busy with things like shipping lanes, military areas which is not possible to do anything, fishing grounds, etc. So the number of routes for cables is actually limited. You can also think of, if it's not possible to develop such cables with such big rating, we might go to other technology developments like high temperature superconducting cables or gas insulated lines. Actually, this is a transmission line within a pipe. These technologies exist, and they are pilots, and there are some projects on the way and realized, but my personal view is that it's more likely that the cable ratings with that high rating will be developed than that we switch to a system with high temperature superconducting and or gas insulated lines. And then of course a lot of accessories should be developed. Then of course there is some requirements on the offshore electricity terminal hub. You must imagine we want to have a power hub of say 2 to 5 gigawatt offshore, and if you see, okay, how shall we do that, why is this the size, you can imagine individual wind turbines will be between 5 and 10 megawatts in future. They will probably individually, they will be clustered in parks with a range of power range of 150 to 250 megawatt, and then we connect a number of clustered parks in so-called strings, and those strings will be connected to hubs. So actually you see levels of power. The macro level, the HVDC supergrid with hubs, big hubs or substations if you want to call them that way, 2 to 5 gigawatt. On a meso scale, medium scale, the HVDC hub power collection strings connecting all those 0.5 to 1 gigawatt parks. And then on a micro scale, individual turbine that can be AC or DC cable connection. And of course there is also the need for energy supply to or from oil gas platforms. They can plug in either on the micro scale or meso scale. Probably they don't reach very big sizes. We envision that these are in the range from 50 to 200 or 400 megawatts. Then I've written down redundancy here. That is because you can imagine if you have a 10 gigawatt cable with a capacity of 10 gigawatt, you don't want to lose that cable. If 10 gigawatt, even with the generating capacity in Europe, 10 gigawatt will give a huge redistribution of the power flow, and can lead to all kinds of overvoltages, etc. So you have to think about the redundancy of that. But then the other way, ladies and gentlemen, if you talk about a redundant 10 gigawatt cable connection, it will be very expensive. Then there are other thoughts. What about the AC and DC conversion stages? Often for wind turbines they generate AC power, often it's converted to DC within the turbine, and then again to AC. If you collect AC, okay, but if we go to DC, then we had another conversion stage, and then of course at the land-based station we have to convert again. So probably we have to think a little bit about that too. Then about the hub function. What, or the hub or the offshore substation, what should it do? By the way, this is a picture you see in it's of course not an electricity hub function, but it is a platform, drilling platform, but they might look like this, I don't know. What should the hub do? It should do the switching and protection of the macro level. That means the big 5 gigawatt hubs should be protected, and the cable. It should be able to accommodate, that means to get the current or provide the current to the local 2 to 5 gigawatt from the macro through connection. That means from the 10 gigawatt cable system, this cable system. Of course, it should do the switching and the protection of the local strings. These strings should be switched and connected and protected, and it should provide communication between the top layer, the macro layer, system-wide, and the several meso layers. So the hub has a number of functions. Basically, these functions, ladies and gentlemen, are not different from ordinary functions which are available in HVDC systems, in power systems. Then the third component will be the mainland terminal. You must imagine, ladies and gentlemen, we talk about mainland terminals of roughly 10 gigawatt, because that's roughly the size we're talking about, perhaps 5, and that's quite a major connection. What is the function of such a 10 gigawatt node? It has to have the function of converting the DC power to AC power at this point, while the AC system is still there in Europe. It has to control the power flow for the offshore network, what's coming from the sea. It also has to distribute the power flow to several AC substations, because it's not feasible to feed in 10 gigawatt into one point. So it can be separated or subdivided into more points, and actually so spreading the load of the substations. And of course it will be very handy when such a hub is located near a heavy load center. And then such a hub, such a node, should also provide some ancillary services for frequency control and reactive power control for the power network. And as I spoke earlier, when you lose 10 gigawatt, then you get a, say if you lose this connection, then you get a significantly redistribution of the power flow on the mainland. You can cope with that either a redundant cable, or an alternative you might guess is reinforce the mainland connections, so that the transmission lines and the substations can handle with that. But either way, it will cost a lot of money. Then, ladies and gentlemen, how do we achieve the transition towards ocean grids? We at the present state have only done some conceptual level studies or visions. There are a lot of them. Recently Greenpeace also made a vision public that says a North Sea electricity grid, revolution or evolution, and I mentioned electricity earlier, and a smart grids platform, but there are more. And I saw from some of you that some of you have also more or less sometimes discussions with customers who are interested in that. But the good thing is, ladies and gentlemen, it has a high level of attention of government and TSOs, of transmission system operators. Transmission system operators, they are very keen at the moment, because they think, okay, what's happening? All those wind farms, in one way or another, have to be connected to our system. And if we don't do anything, what is the present state of the art? Each wind farm a separate cable connected to land. And then you can imagine that you get more and more sort of a spaghetti of AC cables coming into the land. You might get a problem, as typically in the Netherlands, with the number of dune crossings. And you can also imagine that basically this development leads to a technology lock-in. It's cluttered. This gives a huge investment in AC capabilities, and then how to get to the other state. A good thing which is happening, E.ON now is building Borken 2 offshore wind farm in the north of Germany, and they use HVDC light technology, and actually they're building what's called a socket or a plug in the sea where the wind farm can be connected. Or say it the other way around, they extend the grid, the transmission grid, to the sea. TenneT, the Dutch TSO, is doing the same. They prepare for creating a socket in the sea where wind farms can be connected. That makes it for wind farm developers easy to connect, because they don't have to go to all the labor of the dune crossings themselves and the legislation and permits, etc. They can simply connect at sea. Then a thing which is lacking is the modularity of and sea deployable designs, because, as said before, huge investments are needed with this, and people don't invest upfront billions of euros or dollars or any valuta, so there must be a phased investment possible. So investment and financing is among the first requirements, ladies and gentlemen. Then, apart from that, there must be some international agreements arranging for the establishment of the offshore network. How should it be done? Who will be responsible? European and national frameworks, laws, directives, regulation. Who should do the investment? Deep investment, socialized costs, or whatever? Give people licenses to exploit that, or exploit interconnections. Perhaps adapted market rules to better facilitate large energy transaction systems, bigger power flows through Europe. It's possible. And finally, ladies and gentlemen, I will come to you, because I have to watch the time. Hans is very keen on keeping strict to time. Conclusion and future outlook. Basically, the conclusion is that the ocean grid is a key for significantly increasing large amounts of offshore wind energy in Europe. I think this is really what we should aim for. Furthermore, it's perfectly in line with the European policy for the trans-European networks, the 10E. But we need development of sea deployable transmission systems with really large capacities. And I would like to end with a picture of the financial crisis of the end of 2008. I think this might be an opportunity, because, you know, one of the things what's happening with the financial crisis is that a lot of people get unemployed, unfortunately, but again, government are planning to invest huge amount of monies in infrastructural works. United States does so, China does so, and national governments and also the European government can do so if they step beyond the issue of financing banks. Then there will be a bright future, I think, for ocean grids. Ladies and gentlemen, thank you for your attention.